Hi, we are going to talk about acceleration. Now, acceleration deals with velocity. So I have a redundant definition area for velocity. We covered it in the last video on velocity and speed. So, velocity is a vector. And to recall what a vector is, we're dealing with direction again. So, direction plus speed, okay? How fast it's moving in a specific direction. Now, acceleration is going to deal with change in velocity. It's really all we're talking about, okay? When we're talking about a car accelerating from 0 to 60, that's a super common one. There's a specific time frame that can occur. And, something like my vehicle, the 0 to 60 is relatively slow. A very fast one would be like 0 to 60 in 2.5 seconds. But, my vehicle is probably in, 10 to 30 seconds. That's just how it is. But let's talk about how that works. But let's define velocity again. Velocity, of course, is a vector plus speed. However, it's not talking about the change in velocity. So, big difference between the two. Velocity is just a nice plain old vector plus speed, which is direction where it's moving. And acceleration is all of that with change. In the last video, I didn't put in some of my equations what direction it was going after I wrote a velocity, and that was a problem. So in this video, we're going to talk about putting the change in there as well. So let's talk something simple. We did a lot of 0 to 60 type talk, but we need the formula in order to do that. And this formula is relatively easy to think about. We have acceleration, which is A, and this triangle is change in. So I'll write that up here. This equals change or difference, but change in. And then we have velocity. And let's put V over time. And what does change in mean? Because this is the first time we're really digging into change in. Change in is like the two data points you collect. So the data point I collect is 0 to 60. We'll kind of write this right here. 0 meters per second to 60 meters per second. We'll make this big. There we go. And let's say in 10 seconds. Well, let's do 10s. Okay, so this is an acceleration problem. 0 to 60 meters per second in 10 seconds. This can also be known as velocity final minus velocity initial. So there's another thing. So we have more definitions here. V of F, this equals final velocity. You kind of see this somewhat of a coefficient, or rather a bigger letter V, even though it's a small v, and then the subscript of F, that means final. And a lot of mathematicians will use subscripts with initials or acronyms, or you can really write whatever you want. You can write the whole final in the subscript if you want. So it's just kind of a way of organizing your data. And then we have, kind of interrupt this, VI equals initial velocity. Now, this VI, some people also write V naught, which is kind of like what it starts at, but it doesn't matter. Your professor, teacher, etc., will probably be telling you what that is, what the VI or VO or whatever, V naught, however they want to say it's the starting point of the velocity. So we have VF over VI, or VF minus VI over time. Let's plug in what we have down here. So this is also, when I write these equals 2 equals 2 equals 2, well, this is all equal to this A, acceleration. So let's plug this in. So we have V final of 60 meters per second minus 0 meters per second, and we have 10 seconds. Well, that's just 6 meters per second, because that's 60 minus 0 is 60, and that divided by 10 is 6. So we have 6 meters per second, and that's going to be equal to literally what I just said. 6 meters per second is the acceleration. Okay? Pretty swift, pretty easy to understand. Or maybe I just think it is. So let's look at this chart here. I like writing these charts because perhaps this will give us a idea as to how to look at acceleration over a given period of time. So time 1 second, the velocity would be 6 seconds, or the velocity would be 6 meters per second. At 2 seconds, it would be 12, because we're still talking about this problem here. We're still talking about going from 0 to 60 in 10 seconds. This is going to start going off the page a little bit. Okay, at 3 seconds, we're at 18. Okay, so a pattern starting to form here. At 4 seconds, we're at 24 meters per second. At 5 seconds, we're at 30 meters per second. 6 seconds, we're at 36 meters per second. 7 seconds, we're at 42 meters per second. At 8 seconds, we're at 48. At 9 seconds, we're at 54. And at 10 seconds, we're at 60 meters per second. So this is a way to visualize what is happening. Okay? So each second that goes by, the velocity is increasing by 6 meters per second. Okay? So it's getting faster and faster. Okay? The same would work if we were, putting on the brakes. You can look at this going backwards. If we're putting on the brakes and we're going backwards in time, you'll notice, let's say you put on the brakes and it's going to take you 10 seconds to brake. That's a really slow brake. But let's say you go from this 60 meters per second and you want to go on cruise control. So at 11 seconds, you're at 60. At 12 seconds, you're at 60. We're now not accelerating anymore. We're at constant velocity. Okay. Now, all of a sudden, you hit a wall and you're at 13 seconds, you're at 0 meters per second. Okay. So we can kind of visualize what is happening here. Your car was cruising downtown, right? And the next thing you know, you hit a wall. Okay. That's no good. You hit this wall here, and we need to figure out, every car has a black box that records its, a lot of information. So typically a good investigative unit would look at a car after an accident and be like, can kind of find out what was happening in the car. And before I continue, I want to make sure that this is all relative to a vector. So we will write velocity meters per second east. Okay. And if I wrote out my north, east, south, west. Okay, it's really important that we have that, because if we don't have that velocity, well, acceleration in the other way is what's going to occur in this instance here. So this clearly, all of a sudden, there's a western bound force that just completely stops this car from moving anymore, this friction from this wall. So from 12 seconds to 13, so acceleration equals VF minus VI, and then we have time. So from 12 to 13, and I can even put change in time here. Okay, from 12 to 13, so TF minus TI, that's 1 second. And in that time period, the final velocity was 0 minus 60. And the time from 12 to 13, the 13 seconds minus 12 seconds, that's going to be negative 60 meters per second in 1 second. Okay, that's devastating. That's an insane change. And you can almost think of this as a western bound change. Because according to our compass here, I'll rewrite it west and east. The car was moving east. And so this would decelerate towards the western position. Because if I said this was an eastern bound acceleration, well, then you would be adding 60, which that would just mean that this was, this blockade here was actually like a nitro boost or something to a car. But without getting too crazy there, that's how we do basic acceleration in one dimension. Okay. Hope you learned something today, and I hope you have a good day.